So let's start by talking about vectors in situations where we've got equilibrium. So we have met in our work on mechanics this term, we've met forces at an angle, and in a lot of questions those forces have been described with the size of the force, let's say 15 newtons, and the angle at which it is acting, 35 degrees say. And we know that that force has a horizontal component, so when I resolve horizontally, that force has the effect of 15 cos 35. So if that's part of a system of forces, then that's the effect of that force, and there may be another force going the other way or whatever. And resolving vertically, that force has an effect that I can write in two ways. I can either write it as 90 take away 35, so that's 55 degrees. I can either write it as 15 cos 55 or 15 sine 35, the sine of the other angle. So that's, those two things mean the same. And vectors do it the other way round. They describe a force by giving you the two components. And we can therefore use those two components with a little bit of trig and a little bit of Pythag to work out the magnitude and the angle. And vectors are given to us in one of two ways. They're sometimes written in unit vector notation. So 3i plus 2j is a vector of 3 in the horizontal direction and 2 in the vertical direction. So this is 3 and this is 2. Or they write it like this, which is the same thing, but it's just written in a different way. That's minus 2 in the horizontal direction, so that's that way, and 1 in the vertical direction. And you may remember that I always write it in this form because I prefer to work that way. So if forces are described as vectors, so I'm going to draw that first one, so 2i plus 3j, or, sorry, how can I say the right thing, wrong thing, and write the right thing? 3i plus 2j, so that's that and that, so that's what that force actually looks like. So just quickly before we work out the magnitude in exact form and work out the angle for that vector. So leave it in absurd form, and the angle you will have to round. But, yeah, we'll go with degree, shall we? So shift hand at 2/3 and 3 squared plus 2 squared, square rooted. And in some situations, it's much easier to have the picture drawn like this. But in other situations, the vector can be so much easier. The notation looks a bit scary, but actually, because we so often resolve horizontally and vertically, having the value of that force, or the effect of that force horizontally, and the effect of that force vertically, can make things really, really easy. And don't forget, these are forces, so this isn't a journey, this is someone tugging a rope, and the effect is 3 newtons in that direction, 2 newtons in that direction. And it can be easier because if something is equilibrium, those vectors will add up to 0. So in question 5, for example, I know that 3, 2 plus x, which is a missing value, minus 4 plus minus 5 and 2 must equal 0 because I'm told that there's equilibrium there. So it's easy to work out the value of x. So just see if you can have a go at 5, 6 and 7. These aren't in your book, these are in the year 1 version of the book you've got. So just see if you can have a go at 5, 6 and 7. I've started 5 there. Actually 5 and 6 are in equilibrium. 7, there's no equilibrium to start with, but then there is equilibrium. So if there's no J, then it's only acting horizontally. James in. Feel free to go and get a drink or whatever.
I'll be alright.
So where it says resultant force, I suspect they just want the magnitude. I would always do magnitude and angle. I know root 20 is 2 root 5, so well done if you've already simplified that. So, you know, we could, I don't know if in physics you might have done this as a triangle, so you may have drawn this slightly differently, but you should have ended up with the force with the same magnitude and direction. So you could have drawn it as a triangle like that and then a triangle like that, which in the end gave you a line like that. I don't know, is that how you've been taught to do it in physics? Would you have drawn it like that followed by -5, -2, so that's going to be sort of that, and work out your resultant that way? No? Oh, that's good. Right. Are you looking puzzled because I've made a mistake, Charlie? Or? Good, right, yeah. So x is 2 because it just makes that 0, a is -8, b is -1, and then the two new forces on the stone, sorry, you could barely see it, could you? It was for I plus j and f respectively. So, you know, what we're now saying is that they've added 4i plus j plus something else, and it's now in equilibrium. So I've got, so that's a is 0, and b must be 1. So the force is 0, 1. Find the force. So you could say 0, 1, or you could say the force is just 1j. So that's equilibrium. That was last year, yeah, vectors can be used to describe movement, but they can also be used to describe forces, but they can be used to describe any vector quantity. And the other vector quantity that we deal with in this sort of scenario is acceleration. So let's now move on to Newton's second law situations, and let's look at a couple of vector questions which involve vectors for acceleration. So let's. So now we are in year 2. We are in your book, but I'm going to project it all the same. Page number. Right, so we're on page 125 if you are in your book, but don't worry if you're not, because I'm putting it up here. So here we've got more forces described as vectors, but now we're told that there's an acceleration in there. So rather than the vectors adding up to 0, now they're going to give you some resultant force, and that's going to create an acceleration. Now in that expression, force is a vector, because force has size and direction. Mass is not, it's a scalar, it just has a magnitude. But acceleration is also a vector. It has a direction as well as a magnitude. Now, most of the time we're dealing with acceleration in one dimension, so something accelerating along a plane or up a slope or down towards the earth. But it can also be something which is happening at an angle. So in this question 6, we've got a mass of 5 kilograms, and we've got some acceleration, and that's the result of 2 forces being combined. So I'm going to write those 2 forces like this. I've got a 6i and a 4i. and I've got a minus 10J and a 5J. So the resultant force there is 10 minus 5, and that allows me to work out the acceleration. And the acceleration isn't a number times meters per second squared, it's going to be a vector. Which means that this particle is going to start moving and accelerating in that direction. And its acceleration will be 2 meters per second squared in the horizontal direction and 1 meter per second squared down in the negative y direction. So I've used F equals ma with vectors rather than just numbers. I here added the vectors together, which is the equivalent to what we've been doing where we've had forces, we've had 15 cos 45 plus 70 minus 31 cos 40. Now it's all done in vector notation because which is so much easier. So go on, see if you can see what happens in part B where we add a third force. So we've no longer got 2 forces here, we've got 3 forces. They are asking what effect that's going to have on the magnitude. Remember, that's the length of the hypotenuse, the magnitude of the acceleration. And then you've got another question here talking about acceleration, which throws in a bit of Suvat as well. Hi there.
So I have to get an email.
Yeah, thank you for that.
Okay.
It's funny, I've just looked at the data and come up with my list of names, and our Venn diagrams had a very big overlap. So there you go.
Brilliant.
Thank you for that. I'm sorry to imagine.
Have you got compasses?
I have.
Brilliant. Yeah.
And there.
I've got some spares in there.
There's enough for 1 between 2, and then there
You're
are.
going to need one each, probably.
Right. Well, there are some spares
Yeah.
there, and there's some pencils up there.
Lovely.
So yeah, no. You're right.
Okay. Thank you, sir.
No trouble. So in question 6, even without working out any lengths here, I could see that it's going to be smaller, isn't it? It's going to be smaller. So with the third force added, my resultant force is now 4 minus 3. Sorry, yeah, 4 minus 3, which means the acceleration is 4/5 and minus 3/5. And that's what I'm drawing there. So that's not the force, that's the acceleration, the magnitude of the acceleration. So I could draw a picture showing the magnitude of the force, but actually what I'm doing here is showing the magnitude of the acceleration. And that, actually that comes out as 1, doesn't it? So it's 1.